Hello there, welcome to Machine Learning course. This is the third part in the Machine Learning Basics section. So again, 3 of 5. And in this portion, we're going to talk about logistic regression. So without further ado, I'll pull up sort of the slides. So again, we covered first off linear regression. Again, a model that is really a line. And now we're going to shift towards logistic regression, which is probably the simplest model that tackles a nonlinear response or relationship between the inputs and outputs. So we're going to cover that in this third part. Okay, from the true-false test, logistic regression is a combination of linear regression and a tanh or hyperbolic tangent activation function. So true-false, you can kind of test yourself. This is actually false. So hyperbolic tangent is an activation function that is used in neural networks. However, here it's a combination of linear regression and a sigmoid activation function. And we'll show you what that looks like. Okay, so the basics, again, I'm going to put my laser pointer on here. Y, which is our output, is a function of, a new activation function or a new nonlinear function that is, you can see here our linear regression portion. And what does this function look like? Well, it's 1 divided by 1 plus the exponential of negative times this linear portion. And, here's what the function looks like as you put in different x values actually into this. But here we say z, and so as a function of that, it goes from 0 to 1. Never below 0, never above 1. So it's kind of capped within that space. And you would use this for classification problems. So when you're looking at things like the thickness and velocity, if you recall that those were two inputs for a classification machine learning algorithm, and then your response is going to be something like, does the bullet go through or not? Yes or no? So in this case, again, yes, you could put a value of 1. No, you could put a value of 0. So you'd like to have a model that actually goes from 0 to 1 without going, below 0 or above 1. So how do we get this 1 divided by 1 plus the exponential of negative z? So I'll sort of go through what that looks like. I mean, here's an exponential of x. So of course at 0, the exponential raised to the 0th power is 1. And as that power increases, it goes way, way above 1. So exponentially increases. And as it goes down, so negative values, the exponential raised to negative values is going to be, again, 1 over the exponential of, the absolute value of that number. And that's going to go to 0. Now, if you divide that 1 divided by the exponential of x, you're going to actually kind of flip the graph, so to speak. So 1 divided by that, now as you go more negative, you're going to increase the value. And as you go more positive, you're going to decrease down to 0. So these are kind of give you a flavor for where we're going with this. So 1 plus the exponential of x, what's going on there? Well, now you see that you've actually shifted everything up. So now it's going to be, it's never going to go below 1, and it's always going to be above 1. So it's going to increase exponentially from 1 as you increase x. And what does 1 divided by that look like? Well, now because you have 1 instead of 0, at the negative end over here, 1 divided by 1 is 1. So as you go more negative, it's going to be 1. And as you go more positive, you see that it's exponentially increasing. So as it increases to really, really high numbers, 1 divided by that is going to go to 0. And then there's going to be this transition in between. And then the last step is if you do the negative of that number, you're going to flip it. So in this case now, as x goes more negative, it's going to go to 0. And as x goes more positive, it's going to go to 1. When x is 0, it's going to be at 0.5 right in between. And it's sort of a gradual shift from 0 to 1, over this range of, approximately -5 to 5. So logistic regression is going to take actually the linear part though. So instead of just x, let's go ahead and insert our linear regression into that value. So now you have theta naught plus theta 1 times x, so your input. And this would be an example of single logistic regression. And this is called the sigmoid function. But when we get into neural networks, you're going to hear a lot activation function be used. And what an activation function is a nonlinear function that helps the neural network, to capture all these complex patterns. And sigmoid function is an example of one type of activation function. So why not linear regression for these problems? I showed that simple example right off the bat where we had, kind of these cats and dogs dressed in Star Wars outfits, and we actually, if you recall, we had some output responses that went above 1 and went below 0. And what happens with that is since you only have this sloping line, as you have these very high values, the loss function is going to be a lot, right? Because your actual output responses are always going to be 0 or 1 in that case. And so if you get these really, really large values, there's going to be a lot of loss associated with them. And that's going to mean that this line is really going to be distorted by, the extremes. So we definitely don't want that. And logistic regression actually solves that problem, and we'll get into loss functions in a little bit. But before we go there, let's look at, okay, well, we've got this linear part, and you can see that you can extend this to multiple logistic regression. So in that case, again, if you have multiple input features like x1 and x2 and x3 all the way up to the nth x feature, you're going to have a theta value that's multiplying by that or acting on that input feature for each one of those inputs. So, and this is all encompassed within that term that gets multiplied by -1, raised, or the exponential is raised to that power, etc. So what do each of these terms actually do? So theta naught, if you look down here, down below, theta naught, when you go from 0 to 1 to 2, it's actually shifting the whole curve. So this intercept term from linear regression, when put into the sigmoid function, is actually going to shift the whole curve, left or right. The theta 1, so again, the slope term that acts upon these input features, well, what it does is as you increase it, you can see it goes from a more diffuse change between 0 and 1 to one that's much more sharp. And where this comes into play is actually if you have two distributions that are, firmly separated, then it may want to make that a sharp boundary right in between them. But as these two distributions start to overlap more and more, it almost incentivizes that function or that model parameter to become more diffuse in order to, minimize the loss functions. And so what this actually looks like is, here's one with two input parameters and some values of yes and no, whether the bullet goes through. The 0.5 line will be kind of the separation between the two different classes. And then for just one example, or one input variable, here's velocity. So velocity with partial penetration, 0, complete penetration, 1. You can see these are kind of representative of the distributions. And so when you fit a model like logistic regression, you're going to have this gradual shift from 0 to 1 as you try to model this behavior. In this example, again, this isn't the actual line. This is just something that I drew in there to kind of show how it transitions. But you can see the overlap between these two distributions, and that overlap will actually cause the logistic regression model to be more diffuse in order to minimize the loss in the cost function. Okay, so how do we choose these machine learning parameters, the thetas? When you start to shift to classification tasks like this, mean squared error isn't as good of an option. And so one way that you could do this is you could look at your y's, which are your actual responses. These are 0 or 1. And you could look at whether your model prediction, is equal to that. So you could compute your model prediction, you could round to either 1 or 0, and look as an indicator function of whether it captures that. Now, that's not the best way or loss function for these type of problems. And actually a better one, is going to be the cross-entropy loss function. In the case of a binary response like this, where it's really just one output with a yes or no response, this would be the binary cross-entropy loss function. So the binary cross-entropy loss function, if you look here at where my laser pointer is, right in front of the loss, it's going to be negative y times the log of y hat minus 1 minus y times the log of 1 minus y hat. So that's the loss function. And then the cost function is just going to be the average of all of those loss functions. But you may ask yourself, why? Why is it situated this way? What ends up happening is when y is 1, if y hat, the prediction is 1, this log function is going to turn into 0. So, this is 1 and this is 1. They're equivalent. And that whole value, that first value is going to be 0. When y is 1, well, this first term in the second part is going to be 0. So this is all going to be 0 as well. So when they're equal, this is going to return a loss of 0. Now, if y hat is anything else, you're going to have 1 times the log of whatever that y hat is, and that's going to return, a value that's, again, small when it's very close to y, and is going to get larger as you get further and further away from y. And the same thing if you have 0 as a response. So if 0 is a response, this whole first term goes away because y is 0, but 1 minus 0 is going to be 1. So now this is going to turn into 1, and now you want y hat to be 0 as well. So if y hat is 0, then this is the log of 1, and that's going to return 0 and cancel out the term. But if it's anything other than that, the further away it gets from predicting 0, the higher the loss. So that's what's going on with this, cross-entropy loss function which is very common for these sort of classification problems. And I do want to mention that, there's other things that you have to consider here. One of them is related to false positives and false negatives. You can look into precision, recall. There's actually an F1 metric. I just felt like, I should talk a little bit about these sort of things as well. What this maybe one of the disadvantages of using something like a cross-entropy loss term is, when you look at false positives or false negatives, it sort of equally weights these. When in reality, you may want a model that weights these differently. Let's take a cancer diagnosis, for instance. Would you rather be told that you have cancer and it turns out that you don't? Or would you rather be told that you don't have cancer only to find out later that you do? Those two different cases of false positive and false negative may not be equal, and you may want to steer your model towards one or another. And this is often used too, when you have imbalanced classification, where you may have a lot of ones of one class and very few zeros. Your model can actually learn to favor the class that has more output responses in the training set. So here is kind of a joke, but a good machine learning model for 9,999 ones and a single zero response would be a model y equals 1. If you look at the accuracy there, it's 99.99% accurate. It doesn't rely on any inputs there without, in that case. And so you need to pay attention to the fact, like how balanced is a training set, for instance. How well does it predict each of the different classes? These sort of things can be important, and you certainly don't want a model that may be biased in its responses and its predictions. Okay, so with that, that's just a very quick intro into logistic regression. I've got a quick Excel example of, what does this look like? Just so you can get accustomed to, okay, this is how logistic regression is a little bit different than linear regression. So the model parameters here, you can see them up at the top. This is a very simple example. You've got theta 0, so the intercept term, theta 1, the slope term. If you look at your x's, again, we have this column of ones and one input. So our input is velocity. So you can see the velocity here and all these values. Here are the corresponding output responses. So you can see 0 where it's partially penetrating, but it's stopped by the armor. 1 where it goes through the armor. So we want a classification model that can capture this relationship and be used to predict, new input data and what those responses would be. So right now, I also had a column that shows accuracy. It's assuming that our prediction is 0 in this case. So 0 and 0, it gives a 1. It gives a 0 here because 0 is not equal to the actual output. And you get 56% with just predicting y equals 0, for instance. Okay, let's go ahead and Control L. I'm going to start the video and going to narrate while it plays. So here we're going to actually name the different variables. So we'll name that x. We're going to go over here and name the output y. Z is like an intermediate variable. So Z is going to contain the linear regression portion of our model. Here's y hat. So again, the predictions of the model. The loss function is going to be L. These theta values are going to simply be theta. And now we're going to go and build the model. So let's first initialize these values to 0. Matrix multiplication of, and we can just use a variable name, x comma theta. So the same as our linear regression model. Now the prediction is going to be 1 divided by 1 plus the exponential of negative z. So here's how we incorporate the linear regression portion within that sigmoid function. And it's predicting 0.5, which is round up to 1 for the accuracy calculation. The loss function, again, remember, negative y times the log of y hat. I don't know why I use base 10 there, but I just did. You can use a natural log here. Either of those works. So negative y times the log of y hat minus 1 minus y times the log of 1 minus y hat. So you hear me talk about that over and over again. You can see the loss function there. Since it's predicting 0.5, they're all the same, and the cost function is going to be the average of those loss functions. So now we go to the data tab, we go to solver. Again, we're going to select the cost function as that objective function. We want to minimize it by changing these theta parameters, and everything else we can leave the same, and we can go ahead and solve for that using that solver. So we want to keep the solution. And you can see now, the theta values have changed. Our accuracy is actually 89%. You can see that it's capturing a lot of them very well. So that's all the ones means that it predicts, either penetration or stop the same as the actual y column. You can actually go here to the loss function. What did it not get right? You can see here a higher loss function, but it still got it right. Here is a little bit higher, here a little bit higher. If you look across, the velocity on these, 945, 949, 948. So you're actually right in between these two distributions, right? The one distribution of lower velocities where the bullet is stopped, and the one distribution of higher velocities where, it's going to penetrate every time. And there's going to be a crossover point, and the model, has difficulty capturing some of those, probably because, it's a very simple model, what we've done here. So, that's just this example of logistic regression. Turn off my laser pointer. What if I told you that was a neural network? Well, that came quick. Actually, if you kind of look at this, you can look at this as a single node in a neural network. Every node within a neural network has both a linear regression portion as well as a nonlinear activation function. And so the sigmoid function, in essence, is that nonlinear part. So you could even look at this as a very simple one node neural network. And we're going to get into this more as we cover the neural network basics. But just to kind of plant that seed, the logistic regression, it has all the elements that we're going to see again once we go into neural networks. And that's why, we started with linear regression. We went to a simple extension of that logistic regression, which has this nonlinear component. And from there, we can really jump into neural networks and how they're composed. But before we do that, we're going to talk a little bit in these next sections about variance versus bias trade-off and what that is, and also regularization, which will make the model more robust to outliers, and make the predictions better for data that it has not seen. So with that, I'm going to, shift back, to the original screen. And again, thank you for hanging in there. These next couple sections are really going to cover, what is this whole variance versus bias trade-off, which really gets into what does overfitting versus underfitting even mean? You may hear these terms when we talk about machine learning, and that's really where we're going, is like, what is overfitting, which neural networks are very good at. And then what's regularization? Regularization is a way to try to tune the model back from overfitting to bring it to be a more optimal model that does better predictions on future data. So with that, thank you, and may the course be with you.